Alrighty, we're approaching the end of this chapter. We're about to learn a lot more about rational functions. So in the last video, you saw how to graph the most basic one, which was y equals 1 over x. And now we're going to extend that by taking everything that we've learned throughout chapter 8 and applying it to that rational function. So we've learned how to move graphs up and down and side to side by translating them. We've learned how to reflect graphs over the x or y axis or the origin. And then we've learned how to stretch and shrink graphs. And in the course of doing so, we did that to straight lines and we did that to parabolas. So now we're going to take all of those changes, and we can apply them to this new graph, the rational function or the inverse variation function. So before we can do that, there's a couple things we should define vocabulary-wise. So the first definition is a polynomial. So polynomial, we've seen this before a lot in the first semester, but it hasn't been for a while, so I wanted to remind you what it is. It's a sum of terms with only positive exponents. And when I say a sum, that always means adding or subtracting, because if you're adding something negative, then it's still a sum, but you're adding something negative, and it makes it look like subtraction. So a sum is adding or subtracting a bunch of terms, and each one can only have positive exponents. So a simple example would be like 2x squared plus 3x minus 5. Something like that would be a polynomial. Okay? A rational function, which is this new thing that we're learning about, is a ratio, which means you divide a ratio of two polynomials. So you've got one polynomial divided by another polynomial. So the easiest possible case you can have was 1 divided by x, and that's the one that we already saw, y equals 1 over x. That's the simplest possible rational function. But you could have a lot more complicated ones, like y equals 2 over 3x plus 6. Something like that. And so what we're going to learn in this section is how to figure out how you got from this basic inverse variation graph, which is the one that we already know how to graph, and translate it into this more complicated one like this. And interestingly enough, well, let me just use this one as an example. We can write this as 2 over, factor out the 3, and you're left with an x plus 2. And then this is 2 divided by 3, so we can write that as 2/3 in the numerator and x plus 2 in the denominator. Okay, and so this 2/3, it's a multiplying. We start with a 1 and we multiply it by 2/3. So this shrunk to 2/3 of the original size. And this x plus 2 right here, this tells us something as well. Remember, when you're translating an entire graph, use the opposite sign of what you think. So the x variable tells us it's side to side. The plus 2 tells us it's actually to the left. So this means we slid left 2. So if we were to try to graph this, we would think about graphing the old basic one that we already know how to graph. We would slide it left 2, and then we would shrink it by a factor of 2/3. And then we would have the graph without having to do a more complicated t-table or look at this and be like, oh my god, that's some complicated expression. I don't know what to do. It's actually pretty simple. You just take the basic one that you know, and then you slide it up and down, left and right, stretch it, shrink it, reflect it, whatever you need to do. Okay, so we've already done the basic graph. Now we can do something like this. So we'll give some examples of rational functions and their graphs in the next slide. But I want to point out one last thing. The denominator of any fraction cannot be 0. That's something that you learned previously, that you can't divide by 0. So what happens, ask yourself, what's going to happen when I have a 0 in the denominator of a rational function? Because a rational function is a ratio, so it's always going to have a denominator. And so there's always going to be something in the denominator that could cause it to equal 0. For example, this one that we've just done right here. If x were equal to -2, then this entire partial would be 2/3 divided by 0, which you can't have. But I want you to visualize. Let me just make a quick sketch here. Normally, we said that the axes themselves are the asymptotes, and our graph, just a rough sketch, and our graph is going to look something like this, right? So we had an asymptote at x equals 0, which is the axis. But now if we slide left 2, we're going to go 2 units to the left. What that means is this vertical asymptote that we're getting closer and closer to but not ever touching slid left 2, and now it's located at x equals negative 2. So the value that we cannot have is right here at x equals 2, and our new graph is going to look like this. Right there, and right there. So the entire graph slid. I guess for you it'll be this way, left 2. But this vertical line at x equals negative 2 is a line that you approach but you never touch. And it perfectly matches up with this idea that x equals negative 2 cannot be a point on this graph. There is no point on this line. You can get close to it, but you can't actually have it. Alright, let's do some examples. Let's do y equals 2 over x plus 4. So we're going to identify what happened to the base graph to get to this graph, and then we'll graph the new one. So this right here tells us that we stretched by a factor of 2, and this right here tells us we went left 4. Okay, so normally we would start at the origin, and we would have here, let me use asymptotes like I've been doing them in highlighter. So we normally had the asymptotes here and here, but we're moving left 4. So 1, 2, 3, 4. This is going to be our new asymptote right there. Okay. Now we're stretched by a factor of 2. So from the center, you normally plotted the point 1, 1. Okay, let's plot that point. You normally plot the point over 2 up a half, over 3 up a third, over a half up 2, and over a third up 3. And you draw this curve in right here. Let's finish it off on the negative side. Negative 1, negative 1, negative 2, negative 1 half, negative 3, negative 1 third, negative 1 half, negative 2, negative 1 third, and negative 3. So this right here would have been the old graph, and we can label it old since I'm trying to do a better job of labeling things. Well, we don't have the old graph, this is just the new graph. But that's what the old basic graph, y equals 1 over x. This new one has been moved left 4 units. So the new center is here. So we would go from here over 1 up 1. But we've been stretched by a factor of 2. So that means every single point is going to be twice as high. So we would have gone over 1 up 1. Instead we go over 1 up 2. We would have gone over 2 up a half, but we go up double that. So we go over 2 up 1. Over 4, instead of going up a fourth, we go up a half. Over a half, instead of going up 2, now we're going to go up 4. So over a half, up 4. And that should be enough points for me to draw in my graph. Okay. So it looks very similar, but it's just stretched out a little bit. It's a little bit taller. Instead of going up 1 right here, we went up 2. Another thing that you can kind of visualize is that if you double all the outputs, well, never mind, just double all of your outputs. So we would have gone back 1, down 1, and instead we'll go back 1, down 2, twice as far. We go back 2, down 1, back 3, down 2 thirds instead of 1 third, back a half, instead of down 2, we now go down 4. Okay, and I'll draw it in like that. Okay, so this one is the new one here and here. We have a new asymptote, which is this one right here. And again, notice that the asymptote is at x equals negative 4. And what's the one value you can't plug in right here? You can't plug in negative 4 because if you did, you'd be dividing by 0. Let me do, I guess, one last example. Y equals negative 1 over x plus 3. Okay, this negative right here tells you that you reflected over, let's see, you reflected over the x-axis or y-axis. In fact, it doesn't matter. In terms of order operations, you do the multiplication first and then you add 3. So a cool thing, let me just draw a quick sketch. The normal graph is right here and right here. If you were to reflect over this axis, this part would move over here, and this part would move over here, and you'd be left with a curve in the top left and the bottom right. If instead of reflecting side to side, you reflect up and down, This bottom part goes up, and this top part goes down. But in either case, you're going to be left with something here and something here. So reflecting over the x-axis or the y-axis, in terms of the basic graph, has no difference. So we'll just say reflect over the y-axis, and then you apply this change, which is up 3. Now you might be wondering, why is it up 3? I thought we do the opposite sign. This plus 3 here, it's already been moved over to the other side. So before this equation became what it was, you can imagine it might have been y minus 3 equals negative 1 over x, right? And so this y minus 3 really does mean up 3, and then you add 3 to both sides, that 3 is gone, and you can put the plus 3 on this side. So if the vertical shift up and down has been already added to the other side, then you don't have to, in your head, you don't have to change the sign anymore. Positive 3 really does mean up 3. So it's not a y-intercept, but you can think of it in terms of like raising or lowering the graph a certain amount. Okay, so I'm going to draw in my asymptotes first. My normal asymptotes would have been the x and y axis, but I've moved up 3. So my horizontal axis is up 3, and it's now located right here. But I haven't moved left and right, so my vertical axis is still right here, my vertical asymptote. Okay, now we can draw our graph. It's reflected over the y-axis. So instead of being here, I'm no longer here and here. I'm going to be here and here. But the measurements, the amounts, are all going to be the same, and we're not stretching or shrinking because there's a 1 right here in the numerator. So I'll go over 1, up 1, over 2, up a half, over 3, up a third, over a half, up 2, over a third, up 3, and I can draw in my curve just like that. And you notice the line that it's approaching but not crossing is this asymptote. So I think it's very useful to draw the asymptotes in first, and then draw the graph, using the asymptotes as a guide. So we'll go over 1, down 1, over 2, down a half, over 3, down a third, over a half, down 2, over a third, down 3. And you can draw as many points as you want to feel comfortable with it. The more you draw, the more accurate usually it will be. I'd say at least 3, maybe 5 would be a good number to get a nice, good curve in there. And that's what your graph looks like. This is the new one. I'm not going to draw the old one in because it's going to be a bit ugly. You know, I'll draw it in a different color. How about that? Can I pick a different color? Ink color. Let's try, I don't know, light blue. It would have been over 1, up a half, here, here, and here. Just a quick sketch to make sure that you're comfortable with where it would have been. It would be here and here, and then here, here, and here. So the old one in blue here would have been over there. And it got, as you can see, it got moved up 3, and it got reflected. So it switched which side it's on, and it moved up. And that's it. I mean, that's all there is to these. You want to be able to notice what the different changes are. So stretching and shrinking, reflecting, and shifting left and right and up and down. You need to have those memorized so that as soon as you see this x plus 4, you know immediately it meant left 3. And you see this plus 3, you know immediately it meant up 3. The minus sign, you know it means reflected. Numerical coefficient here, you know it means stretched out, or if it was maybe smaller than 1, it would mean shrunk. If you know all those things really, really well, then you can do all your graphs as either a straight line, a parabola, or this kind of inverse variation with asymptotes. It's really important to always draw in these asymptotes. Any of these 3 graphs, you can stretch, shrink, move them all over the place, and you'll be good to go. So the way that you move them is all the same, regardless of how complicated they look.